Welcome back. Everything so far has been governance, watching, and paperwork. Now we roll up our sleeves and interrogate the model directly. This chapter is about testing methodologies, the concrete techniques that turn "is this AI acceptable" from an opinion into an evidenced answer. For many of you, this will be the most hands-on chapter in the course, and it's dense exam territory. Here's our focus map. First, performance testing done properly. Accuracy, benchmark, and regression baselines. Then the sharper tools, segment-level performance and calibration testing, because averages lie and probabilities need honesty checks. Second, fairness testing in depth. Disparate impact analysis, fairness metrics across groups, intersectional fairness where discrimination hides in combinations, proxy variable detection, and the practical toolkits, AI Fairness 360, Fairlearn, and Aequitas, so you know what to ask for by name. Third, testing at the edges. Edge cases, stress testing, out-of-distribution inputs, adversarial testing, and structured red teaming, and the generative AI battery, prompt injection, hallucination measurement, and jailbreak resistance. And fourth, the discipline around it all. Test governance, plans, environments, retesting after changes, connecting straight to Chapter 12, and documenting test results so they stand up as audit evidence. Because a test that isn't documented is a story, not proof. You don't need to run these tests yourself. You need to know what good testing looks like and demand its evidence. Subscribe if you're new, and let's put the machine on the bench. Let's begin with the foundation layer. Three kinds of performance testing that every serious model program runs: accuracy testing, benchmark testing, and regression testing. And the concept that binds them together, the baseline. Get the baselines right, and every later test has meaning. Get them wrong, and you're measuring with a rubber ruler. Accuracy testing you know from Chapter 2, but let's add the auditor's refinements. First, tested against what data? It must be genuinely held out, current, and representative of production. Remember, my fraud model tested against a world that predated digital payments. Second, measured with which metric? And does the metric match the harm, precision, recall, F1, chosen deliberately, not defaulted? Third, compared against what flaw? And here's the underrated question: what's the alternative? A model should beat the incumbent it replaces, the human process, the old scorecard, or even a trivial rule. Remember, 95% accuracy is worthless if approving everyone scores the same. That comparison point is your first baseline. Benchmark testing widens the lens, evaluating the model against standard reference datasets or industry benchmarks, so performance can be compared across models and time. Useful, with a caution you already know from Chapter 11, benchmark seduction. Public benchmarks rarely resemble your organization's data, and models can be inadvertently tuned to them. So treat benchmark scores as context, never as validation. The audit question: does any benchmark used actually resemble the deployment population? Regression testing is the discipline with the longest life because it runs forever. Establish a fixed test suite, representative cases, known hard cases, previously failed cases, and rerun it after every change, retrain, threshold move, prompt edit, everything Chapter 12 defined as a change. The purpose? Catching the silent trade, overall performance up, specific behaviors broken. Mature teams grow this suite like case law. Every incident adds its scenario, so ask to see it, its size, its provenance, and its last run date against the current production version. Now we sharpen the blade. Two testing disciplines that separate professional model evaluation from dashboard decoration: segment-level performance and calibration testing. One breaks the average apart, the other asks whether the model's confidence can be trusted. Both produce findings that headline reports. Segment-level performance first. And you've heard the drumbeat all course: harm hides in segments. Here's the testing discipline behind the slogan. Take the overall metrics, accuracy, precision, recall, error rates, and compute them separately across meaningful slices. Demographic groups where lawful and possible, geographies, age bands, product types, customer tenure, channels, and the operationally revealing ones, low data segments and edge populations. What are you hunting? Variance. A model at 92% overall might run 96% for the majority segment and 78% for a minority one. Same model, different product entirely, depending on who you are. Remember the facial recognition studies? Stellar averages, dramatic failure on darker skinned women? That pattern generalizes everywhere. The audit asks, request the segment breakdown, and if it doesn't exist, that absence is the finding. Then probe the response. Were thresholds, remediation, or scope limits applied where segments underperform? Or did the average absolve everything? Calibration testing is subtler, and once you get it, indispensable. Recall that models output probabilities, 73% chance of fraud. Calibration asks, when the model says 70%, does the event actually happen about 70% of the time? A well-calibrated model's confidence is honest. A miscalibrated one might be systematically overconfident, saying 90 when reality is 60. And here's why that's dangerous. Every downstream decision consumes those probabilities, thresholds from Chapter 1, human reviewers deciding how much scrutiny a case deserves. Remember, automation bias feeding on confident numbers. Testing is conceptually simple. Bucket predictions by stated confidence. Compare against actual outcome rates, and the picture, often drawn as a reliability curve, shows where honesty breaks down. Now we enter fairness testing proper, and let's start with the technique that has decades of legal history behind it, disparate impact analysis. Then build out the modern metric families. This lesson is heavily examined and heavily litigated, so let's get it genuinely right. Disparate impact is a legal doctrine before it's a data science term. From employment law, remember the EEOC lesson? The idea, a practice can discriminate without intending to if it disproportionately disadvantages a protected group and can't be justified by business necessity. The traditional screening test is the 4/5 rule. Compare selection rates between groups. If the disadvantaged group's rate falls below 80% of the advantage groups, the disparity draws scrutiny. Say a hiring algorithm advances 60% of male applicants and 40% of female applicants. 40 divided by 60 is 2/3, below the 4/5 line, flag raised. Two auditors' cautions. The rule is a screening heuristic, not a verdict. Statistical significance and context matter. And passing it doesn't certify fairness, it just clears one crude bar. Modern fairness metrics refine the question. And here's the map. Demographic parity asks whether positive outcomes are distributed equally across groups. Equal approval rates regardless of underlying differences. Equal opportunity asks whether qualified people are treated equally, comparing true positive rates of those who genuinely would repay. Do all groups get approved at the same rate? Equalized odds extends that to error symmetry, both false positives and false negatives balanced across groups. Remember the confusion matrix boxes, now compared group by group. And predictive parity asks whether the model scores mean the same thing across groups, connecting straight to last lesson's per segment calibration. Here's the hard truth the exam loves and reality enforces. These metrics mathematically conflict. When base rates differ between groups, you generally cannot satisfy demographic parity, equalized odds, and predictive parity simultaneously. Choosing which fairness to enforce is the ethical decision from Chapter 9, wearing full mathematical costume. Two advanced fairness disciplines today, and they share a theme: discrimination that hides from simple tests. Intersectional fairness finds bias living in combinations of attributes, and proxy detection finds bias traveling under assumed names. Master both, and you can find what standard fairness dashboards miss. Intersectionality first. And let me show you the blind spot with a concrete pattern. A hiring model is tested for gender bias. Selection rates look fine. Tested for age bias. Also fine. Case closed? Not yet. Break the data into combinations and you find the model performs terribly for older women specifically. A disadvantage invisible in both single attribute views because younger women and older men score well enough to mask it in the averages. That's intersectional bias, harm concentrated at the crossings, and the facial recognition research made it famous. Systems adequate on women overall and on darker skin overall, while failing dramatically on darker skinned women, the intersection. The testing implication is straightforward but demanding. Fairness metrics must run on attribute combinations, not just single dimensions. The practical constraint? Subgroups get small fast, and small samples make noisy metrics. So mature teams prioritize combinations by risk and population size and acknowledge statistical uncertainty honestly. Your audit asks, show me fairness results below the single attribute level, and if every fairness table has exactly one demographic column, you've located the blind spot. Proxy detection we seeded in chapter 10, so let's turn it into testing method. The threat, remember, is that removing protected attributes doesn't remove their signal. Pin codes, shopping patterns, and name-derived features carry it onward. Dropping the column is concealment, not mitigation. Detection techniques to know by name and ask for by evidence. Correlation analysis between each feature and protected attributes, the basic sweep. The more powerful test. Try predicting the protected attribute from the other features. If a simple model can guess gender from your feature set with high accuracy, the information is in there, whatever the column headers say. Theory needs tools. So today, let's meet the 3 fairness toolkits, the syllabus names. AI Fairness 360, Fairlearn, and Aequitas. You won't be writing code with them in the exam hall, but you should know what each is, what it's good at, and, most importantly for your practice, what questions their presence or absence lets you ask. AI Fairness 360 from IBM's research table is the comprehensive one, the Swiss Army knife, an open-source library packing a very large collection of fairness metrics alongside something the others emphasize less, bias mitigation algorithms across all 3 intervention points, pre-processing techniques that adjust the training data, in-processing techniques that constrain the model as it learns, and post-processing techniques that adjust outputs afterwards. Why should an auditor care about that taxonomy? Because when a team says, we mitigated bias, your follow-up is, now precise, at which stage, with which technique, and what did it cost in accuracy? Remember, fairness interventions are trade-offs, and trade-offs need documented owners. Fairlearn, which grew out of Microsoft's ecosystem, is the practitioner's companion, tightly integrated with the standard Python machine learning workflow. Its signature contribution is assessment through disaggregated metrics, exactly our segment-level lesson-made tooling, plus mitigation approaches based on constraints, telling the model optimize accuracy subject to keeping this fairness metric within bounds. Its dashboards make group disparities visible to non-specialists, which matters for governance. Remember, a fairness dashboard viewed only by data scientists is a diary. Aequitas comes from the University of Chicago's policy world, and it's the audit native one, built explicitly as a bias audit toolkit for analysts and policymakers. Its famous artifact is the fairness tree, a decision aid that walks you through choosing which fairness metric matters for your context. Are you worried about wrongly denying assistance or wrongly targeting punishment? Because remember the hard truth, metrics conflict, and Aequitas operationalizes the choosing. Now the audit angles. Presence. Does the team use any systematic fairness tooling? Ad hoc spreadsheet fairness is a maturity signal in itself. Fit. Does the toolkit's application match the chosen fairness definition from our earlier lesson? Tools compute everything. Organizations must still choose. So far, we've tested the model on the world it expects. Now let's test it on the world it doesn't, because production is where weird lives. Three related disciplines today: edge case testing, stress testing, and out of distribution testing. Collectively, the art of finding where the model breaks before reality does. Edge case testing probes the boundaries of normal, valid, but unusual inputs. The 102-year-old loan applicant, the customer with a single character name, the transaction at exactly the threshold amount, the invoice in a rare language. Individually rare, collectively guaranteed. At scale, every edge case arrives eventually. Remember chapter 4? Volume converts the improbable into the scheduled. Good edge case suites are built from three sources: systematic boundary analysis of every input field, production oddities harvested from logs, and incident history. Every past failure becomes a permanent test. Our regression case law from earlier this chapter. Stress testing pushes conditions rather than individual inputs. Volume spikes. What happens to latency and accuracy under 10 times load? Remember, real-time systems degrade in ways batch systems don't. Degraded inputs, missing fields, corrupted data, and upstream feed gone stale. Does the model fail loudly, fail safely, or confidently predict on garbage? That last behavior is the dangerous one. And here's the design question stress testing exposes. What should the system do when inputs are incomplete? Refuse, route to humans, or guess? Someone chose or nobody did, and the test reveals which. Out of distribution testing, OOD for short, is the deepest of the three. It asks, what does the model do with inputs unlike anything in training? The new customer segment, the novel fraud pattern, the post-pandemic behavior, drifts advance guard arriving one case at a time. The uncomfortable truth: standard models don't know what they don't know. They'll score an alien input with the same confident fluency as a familiar one. Connect this to calibration: confidence without competence. Mature systems pair the model with OOD detectors that flag inputs far from the training distribution and route them to safer handling, human review, conservative defaults. Your audit questions: does OOD detection exist? What happens to flagged cases operationally? And was OOD behavior tested before deployment? Ask to see the results. Everything we've tested so far assumed an indifferent world. Now assume a hostile one. Adversarial testing and red teaming evaluate the model against opponents who probe deliberately, creatively, and with intent. This is where testing meets security. Previewing chapter 15, and it's rapidly becoming a regulatory expectation, not a luxury. Adversarial testing first, the technical discipline. The core insight from years of research: models can be fooled by inputs crafted to exploit their learned patterns, tiny, often human imperceptible perturbations that flip predictions. The famous demonstrations: an image classifier seeing a panda, add carefully computed noise invisible to you and me, and it confidently sees something else entirely, stickers on a stop sign causing misclassification. Translate to business systems and the stakes sharpen. Fraudsters structuring transactions to slide under a model's learned boundaries. Applicants gaming the features they've reverse engineered. Remember evasion, coming formally next chapter. Adversarial testing generates such inputs systematically and measures how easily the model folds, producing a robustness profile. The audit questions: was adversarial testing performed for systems facing motivated opponents, fraud, security, content moderation? With what methods? And did results feed hardening, retraining on adversarial examples, tighter input validation, ensemble defenses? Red teaming is the human, structured, whole system version. A designated team, internal, external, or blended, attacks the system the way real adversaries would. Not just the model's mathematics, but the surrounding process, the APIs, the human reviewers, the appeal channels. Remember, the plumbing and the people are attack surface too. The word structured is doing real work. Professional red teaming has scoping documents, defined objectives, which harms are we probing, rules of engagement, documented findings with severity, and tracked remediation. Exactly the governance shape you know how to audit. For generative AI, Red teaming has become the signature assurance activity. Teams competing to make the system produce harmful content, leak data, or breach its instructions. And regulators and standards bodies increasingly expect evidence of it for high-risk systems. Now the audit lens on the program. Independence. Do red teamers report outside the building team? Effective challenge again. Coverage. Are high-tier systems tested on a cycle and retested after material changes? Connect to Chapter 12. Consequence. Sample 3 findings and trace them to fixes. A red team whose findings age in a backlog is expensive theatre. And learning. Do findings become permanent regression cases? Remember, case law. Now we test the systems that talk back. Generative AI breaks classical testing assumptions. Remember Chapter 1. Same input, different outputs, infinite input space, and outputs that can themselves cause harm. So the discipline has evolved its own battery, and today we cover its 3 headline tests: prompt injection, hallucination measurement, and jailbreak resistance. Prompt injection first, the vulnerability class defining this era. The system prompt, remember Chapter 2, it's the hidden policy engine, tells the model who to be. Injection attacks smuggle competing instructions through the content the model processes. A user typing ignore your previous instructions, or, more dangerously, indirect injection, malicious instructions hidden inside documents, emails, or web pages the system reads, so the attack arrives through the data, not the user. Picture a resume containing hidden text telling the screening assistant to rate this candidate exceptional. The recruiter never sees it, the model might obey it. Testing means systematically attempting both direct and indirect injections across every channel the system ingests, and measuring what leaks. Does the model reveal its system prompt, follow embedded commands, take unauthorized actions through its connected tools? Hallucination testing next, measuring the fiction rate. You know the failure from Chapter 1, confident, fluent, wrong, the invented court cases. Testing approaches, benchmark question sets with known answers, scoring factual precision, groundedness testing for RAG systems. Remember Chapter 2? Checking every claim in the answer traces to the retrieved documents. And domain-specific truth sets built with subject experts. The audit questions. Is hallucination measured at all? With what rate? Against what acceptability threshold? And who decided that threshold given the stakes? A creative writing aid and a medical information bot cannot share a tolerance. Jailbreak resistance testing, the adversarial cousin. Jailbreaks are crafted prompts designed to bypass safety guardrails entirely. Role-play framings, hypothetical wrappers, encoding tricks, multi-turn manipulation that erodes refusals gradually. Testing means red teaming the guardrails, remember last lesson? With evolving attack libraries, because jailbreak techniques spread publicly and mutate weekly, which makes this the least once-and-done test in the entire chapter. Resistance decays as attacks evolve, so ask for testing frequency, not just results. Nonce. We've built a formidable testing arsenal across this chapter. Now, the discipline that keeps it from being a collection of heroic one-offs: test governance. Plans, environments, and retesting rules. Unglamorous, decisive, and where auditors separate testing programs from testing anecdotes. Test plans first. A proper plan exists per system, calibrated to its risk tier, remember, proportionality always, and specifies what gets tested: performance, segments, calibration, fairness, edges, adversarial, the generative battery where applicable, against which baselines and acceptance criteria decided before the tests run. Criteria written after results are the definition of motivated reasoning. By whom? With independence for high-tier systems, our effective challenge principle from SR 11-7, and on what cadence. The audit test writes itself. Request the plan, then compare it against what was actually executed. The gap between planned and performed is your first finding. and check who approved deviations. Skipped fairness testing on a lending model is not a scheduling detail. Environments next. Quieter but load-bearing. Testing needs environments that faithfully represent production. Same model version, same configuration baseline. Remember Chapter 12? Same feature pipelines, and data that resembles reality, with the privacy caution from Chapter 8. Production personal data in test environments needs its own justification and controls. And the synthetic caution from Chapter 10. Never validate consequential systems solely on synthetic data. The classic failure. Tests pass in an environment subtly unlike production. Different library versions, different data freshness, and the certificate describes a system that doesn't exist. Ask how environment parity is verified. Configuration reconciliation applies here. Retesting after changes is where this chapter shakes hands with Chapter 12 permanently. The rule: every material change triggers proportionate retesting. Retrains get the full battery. Threshold and prompt changes get targeted, plus regression suites. Vendor model updates, including the silent ones, trigger revalidation. That's why the notification clause mattered. The governance artifact is a change to test mapping. This type of change requires these tests before release, embedded in the pipeline gates where MLOps maturity allows. Your fieldwork move: sample 5 changes from the change log and demand the retest evidence for each, dated after the change, before the deployment. Changes that sail to production untested are Chapter 12 findings and Chapter 14 findings simultaneously. Write them once, cite them twice. The closing principle: testing is not an event. It's a standing institution with plans, real environments, and reflexes tied to change. Institutions leave records, and records are next lesson subject, the final piece, making all of this stand up as evidence. We close the testing chapter where every audit ultimately lives or dies: documentation. Because here's the professional truth: an undocumented test is a rumor with good intentions. Today, what test documentation must contain to function as audit evidence, and how you, the auditor, evaluate it. Start with the evidence standard you already carry from general auditing. Evidence must be sufficient, relevant, and reliable. Then translate it for AI testing. Sufficiency means completeness of the record. And here's the anatomy of a defensible test result. What was tested? The exact model version from the registry and the full configuration baseline. Remember, the model at threshold 70 with guardrail version 3. Results without version identity are orphan numbers. What it was tested with: the test dataset's identity, version, and lineage. Was it truly held out? Was any of it synthetic? Chapter 10's disciplines: reporting for duty. How? The methodology and metrics chosen per the test plan. What happened? The actual results, including the failures and the ugly segments. Selective reporting is the documentation version of rubber stamping. Against what? The acceptance criteria and the pass or fail judgment. And by whom, when, tester identity, independent status, dates, and the approvals that consume these results, connecting straight into the pre-deployment gate evidence from Chapter 11. Reliability is about trustworthiness of the record itself. Results generated automatically by pipelines and stored immutably beat numbers hand-typed into slides. Ask where results live: a test management system or experiment tracker with tamper-resistant history, or a folder of editable spreadsheets. And watch for the reproducibility thread one final time. Can the documented test be rerun to produce the same result? Documentation that supports re-execution is the gold standard because it converts trust me into check me. Now your evaluation craft. Trace, don't admire. Pick one headline claim: the model passed fairness testing, and walk it backwards through the documentation to raw results, then forward to the approval that relied on it. Check dates against the change log. Results predating the last retrain describe an ancestor, not the resident. our museum plaque problem in test form.